Hello students, welcome to Vista's Learning. This is Shruti, your chemistry tutor. We are in 11th standard Vista's Learning. So Vista's Learning provide you the quality education for all. Welcome back and we'll get into our chapter. Do you remember what we are doing now? It's chemistry and we have the exercise part where we are going ahead now. What is the chapter we were doing, students? Do you remember? Yes, it's P block elements and we have already finished the syllabus present in the P block elements and we are going ahead with revision. What do you mean by revision? We need to go ahead with the exercise part. We need to revise the topics what we have already studied. So here are our questions. So are you ready? Let's get into. Discuss the pattern of variation in the oxidation state of boron to thallium. So what is the difference here? Can you get to know? So the answer is here where it comes under 13 group element. Right, students? So P block elements, 13 group element. In that the oxidation state will be +3 to +1. Right. So we'll be having the common oxidation state as +3 and +1. The stability is more for +3 oxidation state as it decreases from boron to thallium. For boron, +3 is been stable where it decreases from boron to thallium as down the group size increases. As size increases, S block elements will be stable. The s orbital electrons present in the outermost s orbital will be stable than that of the outermost p orbital. So one electron they can easily remove, but they cannot have stable +3 oxidation state. Whereas you can see +1 oxidation state increases from boron to thallium. The stability of +1 increases from boron to thallium, whereas the stability of +3 oxidation state decreases from boron to thallium. Down the group, +3 decreases, +1 increases. The next one, carbon to lead. Pb is the symbol for lead, plumbum, right? So carbon to lead, it is 14th group element. We know 14th group element will have 4 electrons in the outermost shell. So here the common oxidation state will be +4, right? But for carbon and silicon, we have seen that it will be having +4 or -4. But general oxidation state for this 14 group element will be +4 or +2. So stability of the +4 decreases down the group where +2 increases down the group. Got it? Good. The next question. How can you explain higher stability of boron trichloride as compared to that of thallium trichloride? Just now we said about the oxidation state which is stable, which is not stable, right? +1 is stable for thallium, whereas +3 is stable for boron. So that is the reason here. Can you get the answer, students? Meanwhile, I'll be back. You got the question? And I hope you are guessing the answer still. Yes, here is the answer. BCl3 is quite stable because it is having its own +3 state, isn't it? So it is stable because there is absence of D and F electrons in the boron. So 3 valence electrons are there for bonding with the chlorine atoms. All the 3 electrons which is present in the outermost shell are available for the bonding. So +3 state is stable for boron and BCl3 is quite stable here. Whereas if you go with the thallium, valence S electron, the outermost shell, the S electron, S electron will have 2 electrons and P electron will have 1, P orbital will have 1 electron, right? So that combining gives you oxidation state of 3. Whereas for thallium, what happens? They are experiencing the maximum inert pair effect because they have d orbital and 10 electrons are more inside, and so what happens, they will have that attraction towards the outermost electron from the nucleus. So that inert pair and that attraction with the inert pair effect, that means it is already paired, it cannot be easily removed. So if we have the attraction, with that we have the inert pair effect, and due to that we cannot easily remove the electrons from the s orbital of thallium. Thus only p orbital electron is available for bonding, and hence the TlCl3 is not much stable compared to that of BCl3. That means boron chloride is more stable than that of thallium trichloride. What does boron trifluoride behave as a, why does it behave as a Lewis acid? What do you mean by Lewis acid and Lewis base? So, boron trifluoride, as we know, it is electron deficient because in the outermost shell we have 6 electrons. To attain the octet structure, we require 8 electrons. So, 2 electrons are deficient. So, it can easily, this boron can easily attract the lone pair of electrons from the donors. So, this is acting as a Lewis acid. So, what is Lewis acid? The molecule which accept the lone pair of electrons will be called as Lewis acid, whereas they can donate, they are called as those who donate the lone pair of electrons will be called as Lewis base. So in boron trifluoride, central atom has only 6 electrons after sharing with the electrons of fluorine atom. So what happens? It leads to the electron deficient compound and behaves like Lewis acid. What is Lewis acid, students? Remember, the gaining of lone pair of electron or attracting will give to lead a Lewis acid. Consider the compounds BCl3, boron trichloride, carbon tetrachloride, and how will they behave with water? So here we are going ahead with the properties of 13 group and 14 group halides and how do they react with water, right? So if I take BCl3 and carbon tetrachloride, so in BCl3 there is 6 electrons. So what happens? It requires lone pair of electrons from the oxygen present in the water molecule, right? So what happens? The octet is incomplete and it can accept the pair of electrons from water and hence undergo hydrolysis, right? So BCl3 undergoes hydrolysis, whereas the carbon tetrachloride, carbon has 4 electrons and it is been sharing. So you will get carbon and 4 chlorine atoms with 8 electrons in the outermost shell of carbon. So it is attaining its octet structure and it is stable. So it is complete, right? It have complete octet structure. So it doesn't require to get any electron or remove any electron. So it is stable and it doesn't react with water. So why it has no tendency? That's why it has no tendency to react with water, means it will not react with water. It don't have even tendency. When do you have tendency? When you have some egarity to gain or lose, right? Here carbon doesn't want to lose the electron nor get the electron. It is already shared and it is stable. It is fully filled. So it doesn't require to react with water. Got it? So we have here carbon tetrachloride with water. We don't have any reaction. So you can say whenever we ask a question, what happens leading carbon tetrachloride with water? If the question mark is here, you can write no reaction. Why? Because carbon tetrachloride, this carbon is having 8 electron, which is completely filled octet structure, and it doesn't react with other water molecules. Next question is boric acid or protonic acid, explain. So what do you mean by protonic acid? So it have to give one proton, like it releases proton. Proton in the sense H plus ions, right? So proton will be released. Is it a protonic acid? But here, if it contains OH, then we call it as protonic acid. If it contains OH molecule, then we can understand that which produces hydronium ion. Then we can call it as it's a protonic acid. The substances which produces the hydronium ion can be easily called as protonic acid. So we'll see here boric acid. What is boric acid? BH3O3, right? So we can also write that formula as BOH thrice. So boric acid is a Lewis acid. What do you mean by Lewis acid? It can gain the electrons, right? So it can easily gain the electron from whom? Water molecules. It is not a protonic acid because it doesn't gives you out H plus ions. So boric acid accepts electrons from hydroxyl ion of water molecule. It accepts the OH minus ions. So if you have BOH, it has still like a deficiency in electrons. 6 electrons are there. So what happens? Water molecule will have OH and this O will come and attack here because it will give you the lone pair of electrons here. So it becomes BOH4. So what happens? One more OH comes and adheres here with this complex having the negative charge. Why negative charge? Because one more O is coming. The boron is having sufficient, it is sharing. If extra electron is been added, then we'll obviously get the negative charge as we are getting over here. And you can see here, we have two water molecules. So one water molecule with another water molecule. So what happens? One OH is been going with boric acid. So what does this H plus will do here? So this will come and attack this water molecule and we get H3O plus. Why we are getting positive charge? Because this is neutral one. We are adhering or adding of H plus ion. So this complete will get as H plus ion, like positive charge. Got it? So boric acid, it will not act as a protonic acid. Explain what happens when boric acid is heated. So when we heat this boric acid, what happens? On heating above 370 Kelvin, it forms metaboric acid. As we know, it becomes metaboric acid HBO2. And further, if you heat it, keep on heating, then we get the boric oxide B2O3. Remember, boric acid H3BO3. Students, BOH thrice is also correct. H3BO3 is also correct. Here 3 oxygen, 3 hydrogen. Here 3 hydrogen, 3 oxygen and 1 boron. Okay. So both are same. So either we can write in this manner, no, or in this manner. So or boric acid, when it is being heated, we get metaboric acid and it is further reacted, we get the boric oxide B2O3. Hope you are clear with this. Any doubts, students? Good. Describe the shapes of BF3 and BH4 minus and assign the hybridization of boron in these species. So we have boron in common with fluorides as well as hydride. Now we need to understand the hybridization of boron in both the molecules. So in BF3, boron will have sp2 hybridization. Remember the students, when we have sp2, sp3, sp3d2. So here, generally we have seen in this chapter these three hybrid orbitals. So sp3 means 2 plus 1. So 3 orbitals, hybrid orbitals will be present. And here 3 plus 1, 4. Here 3 plus 2, 5. 5 plus 1, 6. So what happens here is that 3 ligands can be added to the central atom. Either it might be metal or non-metal. Central atom, 3 ligands will be there. As this one will be like this, that means only 3 ligands can attack to this. Got it? So you will get sp2 hybrid orbitals. sp3 means one more will be there. One more will be there like this. Okay. If it is sp3d2, then we'll be having octahedral structure. Got it? 4 in plane, 1 in the other plane. So this will be called as, you will be having 6, but you cannot call it as hexahedral, but we call that as octahedral structure. Got it? So sp2 will be for 3 ligands. Boron is a central atom in both. So this is 4, this is 3. So if it is 3, sp2. If it is 4, sp3. So in BF3, boron fluoride, we have sp2 hybrid orbitals and the shape will be planar. Whereas for BF4 minus, we have sp3 hybridization and the shape will be tetrahedral in structure. It will be like this. You can also have this trigonal planar where you will be having all the 3 structure like this on same plane. But here it will be on different plane. So we call this as tetrahedral structure. You can see here, this is sp2 hybrid orbitals, whereas this is sp3 hybrid complex. Write reactions to justify amphoteric nature of aluminium. So we have finished boron now, right? So aluminium will act as both acid as well as base when it is being reacted with base and acid respectively, right? So what happens here? It reacts with both acid and base, and so we call it as a amphoteric in nature. So we need to justify with giving the reactions. Aluminium reacts with acid as well as base. Remember this, okay? It reacts with acid as well as base, and that property can be called as amphoteric. What we call it as amphoteric. So aluminium shows amphoteric nature. Aluminium, when reacted with acid, we get aluminium trichloride with hydrogen gas evolved. When the same aluminium reacted with base, both are strong acid and strong base. When it is been reacted with base, we get aluminium hydroxide, tetrahydroxide with hydrogen gas evolved. Right. So what we can say from this? Either aluminium is treated with acid or with base, it reacts. Right. So we get the amphoteric nature of aluminium. Got it, students? Get. What are electron deficient compounds? You should remember this, students. What are electron deficient? So deficient means which is having less. Compounds, the compounds which have less electrons. Less electrons means we should know a particular limit should be there for all electrons, right? So for the outermost orbit of the central atom, they should have 8 electrons. How many electrons? 8 electrons after bonding. If they have lesser than 8 electrons, we call them as electron deficient compounds. If they have same number of 8 electrons in the outermost shell, we call it as electron precise compounds. If it is more than that, for example, 10 electrons are there extra electrons are there in the outermost shell after bonding. So that we call it as electron. Now we have deficient, right? What we call it as excess, right? So electron excess compound. So you should remember this. BCl3 and silicon tetrachloride are electron deficient species or not, we need to explain. So electron deficient species are those which have the central atom in their molecule which has the tendency to accept one or more electron pairs. Why? Because they'll be having less number of electrons in the outermost shell, so they can gain one or more pair of electrons. They're also called as Lewis acid as they accept one or more lone pair of electrons from others. BCl3 and silicon tetrachloride both are electron deficient species. In BCl3, boron has only 6 electrons in the outermost shell and it is an electron deficient compound. In silicon tetrachloride, the central metal has 8 electrons, but it can expand its covalency beyond 4 due to the presence of d orbital. Its covalency can be increased from 4 to extra. So it can accept the electrons. So it should be considered as electron deficient species. They are saying, got it? So BCl3 is a electron deficient species, but for silicon tetrachloride, it has electron, 8 electron. It is electron precise, but the exception is that that will also accept the electron because it has d orbital, vacant d orbital. It can easily gain the electron and it can extend its covalency beyond the 4. So what happens? They can also be considered as electron deficient species or compounds. Okay, that is the exception. These are some of the exceptional cases. Write the resonance structure of carbonate and bicarbonate or hydrogen carbonate ions. So here is the first one, carbonate. What happens? C double bond O and single bond O will be having like this. So they will be having -2 charge, right? Because carbon can have 4 bonds, whereas the oxygen should have 2 bonds each, where here one bond is missing and here one more bond is missing for this oxygen, right? So what happens? This will be having 1 electron, this will be having 1 more electron, which gives you -2 charge. So we have the movement of electrons. What do you mean by resonance? Means the d orbitals or the electrons, pi electrons can be easily shifted from one atom to another. So the shifting of this delocalization of electrons will be called as resonance, and the structure formed at every instance will be called as resonant structure. So you can simply understand this: one oxygen atom, second, third, 1, 2, 3, 1, 2, 3. So now the carbon will be having the double bond with the first oxygen atom and single bond with the second and third one. What happens? This will be shifting towards the third one, right? So here the bond shifts and oxygen lone pair will shift to the first one. And next, this will shift to the second one. So this will shift, the bond will be shifting and you will get the double bond here. And you will be having the bond like this. So what happens when you have this resonance? The stability will be more resonance structure, more stability. So I can just show you this. So you will have negative sign like this, and this the electron negative charge will come as the double bond and this will shift back. So we'll get the carbon as O minus, here double bond O, and here O minus. Then what happens? This will shift as a double bond and this will go back as a minus. So C O minus, here O minus, and here double bond O. So these are the three structures which are there for carbonate ion. You can ask me, all the three are similar, no ma'am? Yes, that's why we mentioned here 1, 2, 3. Three different oxygen atoms. Each one can shift the bond and get back to the negative charge. Shift the bond and get back to the negative charge. So that will be continuously doing, and hence we call this is stable. If you have more resonance structure, that will be more stable. Next, you have here where you have only two structures for bicarbonates. Why? Because if you have bicarbonate, the one negative charge will be here, double bond O, and one more O will be here. So two negative charge will be there. So this negative charge will be attracted by hydrogen and they form a bond over here. So this negative charge is stable now. Only you can convert this to this. So what you can get is that O minus, here double bond O, and here OH. So only these two resonance can be seen in the bicarbonate. So what happens? We have two resonance structure for bicarbonate, whereas three resonance structures for carbonate ion. Hope you understand this, students. Good. What is the state of hybridization of carbon in given substances? The first one is carbonate ion. How many bonds were there in carbonate ion, students? We have C, double bond O, single bond O, and single bond O, right? So it should have sp. See, one bond, one bond, one bond, sp2. One more bond is pi bond. Got it? So double bond means multiple bond. If it is all the single bonds will be sigma bonds, whereas the double bond will be pi bond. If it is a pi bond, then you can consider it as a sp2 hybrid orbitals. For diamond, it will be sp3. Why it is sp3 for diamond? Diamond, what happens? You will be having the carbon and other 4 carbons like this. So one carbon is linked to the 4 different carbons, making each a single bond. So 1 sigma bond, 2, 3 and 4. So 4 sigma bonds are there. Hence the hybridization can be taken as sp3 hybrid orbitals. Whereas for graphite, we have layers in the graphite. They are hexagonal layers where you can find this 1, 1, 2 and the 3. You will be having the 3 bonds with the sp2 hybridization with other carbon atoms. So graphite will have sp2 hybrid orbitals. Next question. Suggest reason why BF bond length in BF3 is 130 picometer and BF minus is 143 picometer. So here bond length we are speaking. The length is very short. Shorter the length, attraction is more. Longer the length, attraction is less. In BF3, what happens? sp3 hybridization has been taken place, whereas in BF4 minus, that is 4 minus, what happens? We have sp3 hybridization. So this sp2 and sp3 hybridization will make you the difference. Why? Because sp2 will have the planar where the bonds can be easily stretched, right? If you go ahead with the same one, fourth one, what happens? For example, if we are taking triangle, so what happens? If we go ahead with this, the bonds which has been formed in the same angle, like a same plane, if they are all equal, so what happens? You will get 120, 120, 120 each, right? But if I take a square, what happens? So from here it will be 90, 90, 90. Even though they are equal, it will be 90, whereas here it is 130. So here hindrance will be there. The space will be congested. So what happens? They move far. When they move far, the length will increase. The bond length increases. So what happens here? The difference in the bond length is due to the state of hybridization. So if you have sp2, then it will be in the same plane. So bond length will be less. So you have 130 picometer for boron trifluoride, whereas for boron tetrafluoride, we have 143 picometer due to the hybridization. Suggest a reason as to why carbon monoxide is poisonous. We should know this, students, because it is very much important. Even in our daily life, we'll be saying carbon monoxide releasing of, we burn more of fuels like petrol, diesel, and even other products. What happens? They releases, if we are going ahead with incomplete combustion, they releases carbon monoxide, and that is very poisonous. That we need to know. Carbon monoxide reacts with the hemoglobin to form the carboxyl hemoglobin. I have a hemoglobin in the blood. What happens? The oxygen will be there. O2, okay. If carbon monoxide is entering inside, it can easily displace this oxygen and become carbon monoxide. The oxygen can be easily removed out. Getting this point? So what happens? The absorption of carbon monoxide by the hemoglobin is more high than that of the oxygen. So the carbon monoxide reacts with hemoglobin to form carboxyhemoglobin, which can destroy the oxygen carrying capacity. We require oxygen, living organisms require oxygen. When carbon monoxide has been attacking, oxygen will obviously come out. Then the sufficiency or production or oxygen present in the body will automatically reduces. So what happens? The oxygen carrying hemoglobin will be cancelled or they will be destroyed. So that makes the man to suffocate or it may lead to death, because every minute we require oxygen, right? If oxygen enters into our body, respiration takes place, and respiration, chemical formula of respiration leads to the given like a evolution of energy, and that energy in turn makes the body to do the metabolism, right? So if oxygen is not there, the energy will not be released. If there is no energy, no work will be done. So automatically the heart stops beating and man can lead to death. Got it? So it is very poisonous. Be careful. Explain the structure of diborane and boric acid. Boric acid contains planar BO3 3 minus ions which are linked together through hydrogen bonding. So you can see here, this is the one structure where you can see the boric acid, H3B3O. So one boric acid will be combined with the other by hydrogen bonding. So they have the hydrogen bonding with other hydrogen and oxygen atoms, which leads to the formation of this structure. So due to hydrogen bonding, we have this structure of boric acid. Whereas diborane, if you see, the boron is having just BH3. But due to the hydrogen bonding, again they come closer to form B2H6. So the structures of diborane and boric acid. This is the diborane, which is due to the hydrogen bonding. This is the boric acid, which is due to the hydrogen bonding. What happens when borax heated strongly? So borax is sodium borate, Na2B4O7.10H2O. When it is being heated, all that 10, that is decahydrate, that 10 molecules will be easily removed out, and you will get this excuse me, anhydrous borax, right? Then further if you react, you'll get boric oxide. Excuse me, students. Next we have boric acid, which is added to water. We know this boric acid, when added to water, we form the hydroxyl ion will be added to them, right? With the evolution of hydrogen gas. And next we have aluminium treated with dilute sodium hydroxide. Aluminium reacts with base, aluminium reacts with acid, we saw, right? So it is reacting with base to form sodium aluminate with evolution of hydrogen gas. And we have BF3, which is reacting with ammonia. BF3 acts as a Lewis acid, ammonia acts as a Lewis base, and they combine together and form this complex. Got it? This arrow mark you should remember, students. Lone pair of electron present on the nitrogen will be donated to the BF3 boron. Explain the following reactions. Silicon is heated with methyl chloride at high temperature in presence of copper. So what happens when the silicon is added? Silicon is heated with methyl chloride. So in presence of copper powder, that is the catalyst, and at higher temperature around 373 Kelvin, we get this equation where mono, di, trimethyl chlorosilicanes are formed. So here you can see one silicon is added, Cl3 is been added with that one, mono, di, tri, and we have this monoditri methyl chlorosilicanes which is been formed, and we also have small amount of tetramethylsilane which is been formed. Are you getting this point, students? Silicon, when it is been heated with methyl chloride, we get methyl monodichloro CH3 Si Cl3. So this is what which has been formed, and if you want di, it will be CH3 twice. If it is thrice, CH3 thrice, 4, then CH3 4. And you have to remember by that time this chlorine will be reducing to 2 and then 1 and 0 respectively. Okay. So here we are getting methyl chlorosilane. So dimethyl chlorosilane, trimethyl chlorosilane and tetramethyl chlorosilane will be formed when silicon is being reacted with methyl chloride at higher temperature around 373 Kelvin and in presence of copper. Next, silicon dioxide is treated with hydrogen fluoride. Then what happens? Initially what happens? Silicon tetrafluoride dissolves in hydrogen fluoride to form hydrofluorosilicic acid. So this is the hydrofluorosilicic acid which has been formed. So silicon dioxide when reacted with hydrogen fluoride, we get like silicon tetrafluoride. When further reacting with, then we get hydrogen fluorosilicic acid. Next question is carbon monoxide heated with zinc oxide. When zinc oxide is treated with the carbon monoxide, zinc is a metal, right? So what happens? It reduces to zinc. Carbon monoxide takes the oxygen and forms carbon dioxide, and zinc will be given back. So this process will be used in metallurgy to reduce the metallic ore to metal. Next, hydrated alumina is treated with aqueous sodium solution, sodium hydroxide solution. So alumina dissolves to form sodium meta-aluminate, as we say, the hydrated alumina or bauxite. Al2O3.2H2O is its in form of oxide form of alumina which is present as a ore, and we have the bauxite which is ore present for the aluminium, from which aluminium will be extracted. When that is been reacted with the base, obviously we know aluminium will react with base, so its oxide also reacts with base to form sodium meta aluminate with releasing of water molecule. Next question. How do you explain the lower atomic radius as lower atomic radius of gallium as compared to that of aluminium? We know down the group what happens? The size increases. So boron, aluminium, gallium, and then if you have aluminium and gallium, if we are considering this, next you have indium. When you consider this aluminium to gallium, aluminium is in second group elements, whereas gallium is in third group element. So d orbitals are present in, so we can say that poor shielding effect of d electrons in gallium means it will be having the d electrons and their shielding is very less. The d orbital electrons will be shielding very less. Due to that, what happens? Excuse me. Electrons in gallium experience a great force of attraction by nucleus as compared to that of aluminium. So, I'll say you, when you have the gallium, you have the electrons present in the inner core. So, these inner core electrons will not shield, will not cover completely. So, that shielding effect is less. So, what happens? Nucleus can easily attract the electrons from the outermost orbit. So, gallium, in gallium, it can easily attract the electrons, and d orbital which are present in the electrons present in the d orbital are not sufficiently shielding. So, since they are not shielding, nucleus can have the attraction towards the outermost orbit easily, and so attraction is there. Due to the attraction, the size decreases, but there is no such poor shielding for aluminium, so it has a larger radius than that of gallium. Next question. What are allotropes? Yes, students, you have two things to remember: isotopes and allotropes. Isotopes are different, allotropes are different. Isotopes depends on the number of neutrons present in the nucleus of each atom. But allotropes depend on the hybridization and the structure and their form physically, how they are formed in the earth's, found in the earth's crust. Got it? So what are allotropes? Sketch the structure of two allotropes of carbon, namely diamond and graphite. We need to get the structure of diamond and graphite. And what is the impact of structure on physical properties of two allotropes? Either it is isotopes or allotropes. Both have the physical properties in different but not the chemical properties, because in isotopes what happens, number of electrons present in the outermost shell matters. So for both isotopes, what happens, for both carbon 13, carbon 12, carbon 14, outermost electrons will be same. Since the electronic configuration is same, the chemical compound, chemical properties will also be same. But here in allotropes, since they have the same number of atoms and same number of electrons present in the atoms, but just the structure differs, they have the physical properties different and same chemical properties. Allotropes are different forms of an element which are having same chemical formula but differ in physical properties due to their structures. Got it? In diamond, we have the carbon with sp3 hybridization, and since the diamond is three-dimensional network solid and it is hardest substance. As we said, it will be in this manner. So it will be bond with each carbon atom. One carbon atom will be bonded with each adjacent 4 carbon atoms, and it will be having a very good bond. So very strong bond. And here we have the 3-dimensional structure of this sp3 hybrid atom, and that increases the hardness of the substance with high density, whereas graphite has a layered structure. Graphite will be having the layered structure as we saw in the previous class. You can see it will be having the layered structure like this. One layer here, one layer on the other one. With oxidation, with the hybridization differs. So the variation or various layers are formed by van der Waals force of attraction. It is very weak. Weakest force of attraction is van der Waals force of attraction. In between each layers, we have the van der Waals equation, and hence you can just write on the paper with a pencil. Why? Because you can just apply a very less amount of energy to remove these layers. So that is the weakest force of attraction present, which we call it as van der Waals force of attraction, which is present in between the layers of graphite, and that makes the graphite very soft and slippery. It can be used as a graphite can be used as a lubricant because of this slippery property, or it will be not having a very hardness or rigid substance. It is not a rigid substance where the layers can easily be removed by adding very less force. So you can see here, this is the structure of diamond where one atom of carbon is been bonded with 4 other adjacent carbon atom. If you take this oxygen, this is again bonded with 4 different carbon atoms. So if you take this again, it will be bonded with 4 different adjacent oxygen carbon atoms. And if you take any one of them, they will be bonded with 4 different adjacent carbon atoms, and this structure, how it is been formed, that makes the diamond very hard and also high dense. Its bond length will be 154 picometer, whereas for graphite you can see it will be hexagonal layers. One is the layer here with 141.5 picometer, whereas this distance between the layer, one layer to the other layer, will be 340 picometer. Easily you can apply the small force and remove this or the outer layers. So this is the structure of graphite. Next question. Classify the following oxides as neutral, acidic, basic and amphoteric oxides. They have given you the list of oxides, right? In that, which is acidic, which is basic, which is amphoteric and neutral, we need to say. So here, as we have already discussed about this, you should be knowing. And the second question is write suitable equations to show their nature. Fine. So here, carbon monoxide, boron, diboron, dioxygen, and silicon dioxide, carbon dioxide, aluminium oxide, plumbum like lead oxide, lead dioxide, thallium trioxide we have. So in this, neutral one is carbon monoxide alone, and we have acidic property which has been exhibited by B2O2, SiO2, CO2, because when they are mixed with water, they directly convert into, they give you the acidic nature. Whereas basic one are thallium trioxide and amphoteric. You can also say about this amphoteric as aluminium trioxide and lead dioxide. So it should be aluminium dioxide. Okay. So thallium is basic because thallium is the largest element in the given group. So what happens? It will be more metallic in nature. Metallic in nature means it will be having basic oxide. Whereas aluminium is amphoteric in nature, hence its oxide will be amphoteric in nature. And carbon monoxide does not react with acid as well as base at room temperature. So we can consider it as a neutral substance. So if it is reacting both with acid and base, we can consider it as amphoteric in nature. And these being the oxides, they react with alkalis, that is base. These three reacts with base to form salt. So they are considered as acidic in nature. Whereas thallium oxide, which reacts with acid to form base, and it reacts with acid to form salt, and hence we can consider it as a basic in nature. Whereas amphoteric, aluminum and plumbum, if you see, they react both with acid and base, and hence they are called as amphoteric in nature. So boric acid reacts with base and gives you the sodium borate. So silicon dioxide reacts with base to form sodium silicate, and carbon dioxide reacts with water like sodium hydroxide and gives you sodium carbonate. And the amphoteric one, aluminium and lead oxide, when they react with base and acid, you will be having the salt which is been formed, which shows that they are amphoteric in nature. Likewise, lead, which is reacting with base and acid, gives you the sodium plumbite and lead sulfate. So this gives you the formation of conformation of amphoteric nature of aluminium and lead oxide. And thallium oxide dissolves in water, they dissolves in acid and forms thallium trioxide, which shows that they are basic in nature. Hope you understand this, students. You need to remember, when these oxides given, when they react with acid, what happens? When they react with base, what happens? If they are not reacting with base, then they are acidic in nature. If they are not reacting with acid, then they are basic in nature. If they are not reacting with base or acid, then they are neutral. If they are reacting both with acid and base, then they are amphoteric in nature. Got it? Next, what do you understand by inert pair effect and allotropy and catenation? Okay. Allotropy just we saw, right? What do you mean by inert pair effect? The pair of electrons in the valence shell, outermost shell, does not take part in the formation of bonding. If I have two electrons in the outermost shell and in p orbital I have one electron, only this one electron is taking part in bonding and these two are not, then they are inert. Inert means they don't react. So they don't participate in formation of bonding, then we call it as inert pair effect. Either you can have two electrons or three or n number, all the 6 numbers also, or if you have 5 numbers also, what happens? Outermost s orbital electrons, if they are not reacting, then we call it as inert pair effect. What about allotropy? As we said, it is the property of the element to form many or different structures. It has been available in different forms. So, two or more forms which have same chemical properties but differ in physical properties due to their structures. What do you mean by catenation? What do you mean by catenation here? So, any cat has been formed here or any cat has been involved? No, here when we speak about catenation, it is a property of carbon. So, the property of forming chains or rings not only with single bond but with double, triple bond with the same element and the other element also. It can form triple bond or double bond with other elements as well as itself. If it is forming the bond with itself, multiple bonds with itself and forming the long chains and rings, then that property can be exhibited or called as catenation, and that can be exhibited by carbon atom. So example, carbon forms long chain by single bond as well as with the multiple bonds. So we have the hydrocarbons group which contains all the three alkane, alkyne and alkenes. Why is boron used in nuclear reactions? It is easy that in nuclear reactions, neutrons will be released that can be easily absorbed by borons to stop the reaction, and we can say that is the reason why boron is used in nuclear reactions. Why does boron form stable electron deficient compounds? Boron has 3 electrons in its valence shell, and that shows 3 electrons with the other elements and form an electron deficient compound. Means it will be having all the 3 electrons which has been already paired. So it will be stable. But it has 2 more electrons deficient for attaining the octet structure. Hence, we can say it is a stable electron deficient compound. Next question. By giving balanced equations, show how BOH thrives. That is, boric acid behaves as an acid in water. So, when it has been reacted with water, it accepts OH minus ion and forms the BOH4 minus while releasing the hydronium ion. So, it behaves like a acid in water. What is the basic building unit of all silicates? SiO4, 4 minus is the basic unit of silicates. That means you will be having silicon with all the oxygen atom linked, all the 4 oxygen atom linked with the silicon with single bond, and each oxygen should have 2 electrons. But here it has been linked with only one single bond with silicon. Hence you have 4 negative charge each. So we can write SiO4 4 minus. So this is the basic unit for silicates. Why do boron halides form addition compounds with NH3? Because since it is electron deficient, they can easily accept the lone pair of electrons. So boron halides are Lewis acids and can accept lone pair of electrons from amines to form addition product. So by this, we finishes this class students, this chapter, P block elements. Next, we are going ahead with very interesting chapter, organic chemistry, that is hydrogen, hydrocarbons, where hydrogen and carbon combining together to form a longer chain we discussed, right? So that hydrocarbons we are studying in the coming classes. Thanks for watching Vista's Learning. If you have missed any of the video students, you can browse into www.v-learning.in. If you have any doubts, get back to us. We are always here to help you with your studies.